Reverse engineering ransomware protocols. Dharma. Now you're gonna dance, right? Okay.
Okay.
Anyway, here we go.
Cool. So I'm going to start out quick intro. Who am I? Why does anyone care about what I'm saying, right? So I'm Kyle Nehman. My email's up there. If anybody's got any questions about anything, feel free to reach out. I'm product lead at Cyber Crucible, local cybersecurity company, but not going to talk about that too much. I'm a little bit of a self-proclaimed ransomware expert. One of those things where I start talking, I call myself an expert, someone else calls me an expert, and now that's what I am, right? So my background is a little bit of threat hunting, malware analysis, low-level kernel development, back-end development, things like that. Lots and lots of encryption kind of leads you right into ransomware, right? So a quick kind of intro to the talk is that it's very technical. It's a lot of like staring at hex editors type of thing. I call it dynamic analysis as opposed to static analysis because for those familiar with the two terms, static analysis refers to like using Ghidra, IDA-Pro, something like that to look at like functions that are in executables. This is not that. This is looking at the protocol itself, especially on disk, right? So it's going to be insight into Dharma ransomware specifically, and kind of the discovery, a little bit of the story of like how you go from, oh crap, I was hit with this ransomware, to understanding what happened on your disks, right? It's definitely not the secret to free decryption or anything like that, obvious, but I kind of got to say it because otherwise someone's going to say, okay, well, you can save me millions of dollars, right? We'll see, but probably not. So, and the why do you care, of course, is you can figure out how bad your situation is if you're involved with this ransomware. You get a little bit of insight if the attacker's kind of manipulating you, trying to get more money for no reason, all that kind of thing. You can figure out if you can even decrypt, if it's even possible, and how much it'll cost you, all sorts of things like this. So, again, it's going to be pretty technical, but hopefully everyone can get a little bit of insight out of it. So, first question should be, what is Dharma? It's a Windows-based ransomware. It's C++, though that doesn't matter at all. It's statically compiled, which means that we can't just look at DLLs, see what it's doing. There's no like API monitoring because it's all built right in. It's very strongly encrypted. It uses like the best encryption standards out of any ransomware. Many of them use good standards, but it's up there with the best. It's AES encrypted for all the files, which is very fast, of course, and then RSA encrypted. If you don't know what those are at all, it might suck, but I'm going to explain them quickly. I don't want to spend too much time, though. And the ransomware itself uses a two-step process. So you scan your system, you send the output to the attacker, you pay the ransom, and then they're going to send you back a decryptor. If you're wondering why there's JavaScript on the right-hand side, me too. That was the first image result on Google when I searched for ransomware. It kind of doesn't make any sense, but that's part of the problem. No one understands what's going on when they're searching for answers. So something more relevant might be like a ransom note for this ransomware. You probably can't see it too well, but it's it's just all your files are encrypted. Send Bitcoin to this address type thing, right? So, quick explanation of AES. It uses CBC, which is a type of blockchaining or block cipher. So it just kind of goes through one to the next, and you keep looping in 128-bit blocks. All you need to know if you don't care about the implementation of it is that it's symmetric, means that both ends have to use the same key. It's a 256-bit key, which is really secure. It's very fast, and all we need is like the key, the padding, the IV, basic information. RSA, on the other hand, asymmetric encryption. The two parties involved have different keys, private and public, also super secure, but much slower. So if you ever see people say that ransomware uses RSA, it probably does, but it doesn't encrypt every file with RSA. It's way too slow, right? It's going to use AES, something fast, maybe Cha-Cha, whatever, and then come back and encrypt the keys for the first algorithm with the second algorithm, right? So getting into the really dry technical stuff a little bit, a lot of it actually. What does it look like? So I've opened here in a hex editor. You can see this is an encrypted file. It means absolutely nothing to anyone, right? You're looking at random data. But if you can see, and this is the beginning file on the left and the end of the file on the right, you can see on the right-hand side there's English readable words. It's actually the file name, right? Driver installation log.txt. And this is, everything here is real sample data. It's been changed a little bit so that there's no sort of like concern about client data being leaked, but it's a real ransomware sample, real data. So we can look at the file name and we can say, great, That's the file name. Who cares? It doesn't get us anything. What's after the file name? Because we have to start somewhere. There's some zeros, it's a delimiter, right? Doesn't mean anything by itself either. And then you can kind of keep looking and say, let's compare two files. Do they do the same thing? Is the file name in the same place? What follows? Let's really compare and contrast. So, same thing, open a separate file, favicon.ico, same thing, file name's there, and we don't know anything else about it. But we can see, here's where the similarities start, right? They both got this kind of weird identifier after them. Also, English readable, might be coincidence, who knows, but it's there in both, so we know there's at least a similarity. It's not just complete randomization, which is good because we're trying to find a solution. If we keep looking, we'll notice that it's actually not just the English readable part, it's actually this big string of bytes. What they are and why they were generated by what algorithm, not important, right? What's important is that they're the same in both. They're serving as kind of like an identifier. Something here is telling us more about what's going on. We can start to say, okay, if these parts are similar, are there other parts that are similar? Maybe you can start to get an inkling of like reusing keys, something like that. That's jumping a little forward, but that might be what's running through your mind when you're trying to actually, save your client here. You're like, oh, maybe there's hope. And then, your hopes are dashed because immediately you notice that after that, 20 bytes or whatever it was, they're completely different again and nothing's the same. So, the questions that you're asking here, the whole point of looking at these files again is like, how bad is the damage? Is it actually encrypted? Because sometimes, you get hit with ransomware and it's not really encrypted. It's like XORed or zipped or something stupid, or they changed the file name. In this case, you're trying to figure out, is it encrypted? What kind of encryption? All that kind of stuff. And we've run out of things to look at here. There's nothing more, right? It's all random data except for the file name. So I mentioned a file scanner earlier. With it being a two-step process, the way this works is Dharma infects my machine. I can't open any of my files. They're all encrypted. The hacker has given me generously, of course, a file scanner, and they say, scan your PC, paste me the output from scanning your PC, and then, pay the ransom, and I'll give you the data back. So now we're going to start looking at the file scanner because looking at the files by itself, totally not useful. Again, not static analysis here. But so we're going to look at the output, say click scan PC, see what the output is. And this is a sample output of file scanner. Again, some of you are going to recognize this, hopefully, base64. It's just encoded data. So then we can actually just spit it into a base64 decoder. CyberChef, a tool, if you're not familiar with, I super recommend it. It can do tons of stuff, and it's really useful as just like a notepad kind of thing to do encryption, decoding, manipulation of bytes, all kinds of stuff, in a web UI. CyberChef's not the point, though, right? So paste in the base64. You can see I'm converting from base64 to hex, and the output's on the bottom. I'm just going to blow it up. Same output, same exact thing. So again, more bytes, right? We don't know what's going on, what we're looking at. The important thing here, though, is that we can start to look for some identifiers and some things that you might recognize. And to me, the first thing that's obvious here is that these are kind of little endian integers. And to just give another brief explanation of what that means, because some people are going to be different levels of technical, little endian is kind of when the bytes are stored in reverse order. So this first one, 02000, is actually just a 2, because you kind of read it in reverse. And we know they're integers. We suspect they're integers because it's 32 bits, right? It's 4 bytes. So what we're trying to do here is just glean some sort of structure out of this data. We know, obviously, if the attacker needs it, it's not just random, it's not just a key, it's not, whatever. So we want to know what kind of information we're providing to them, for one, because how are they going to use it? 2, how are they going to manipulate it? And 3, can we get some extra value out of it? Or are we going to lose data? You talk about, getting hit twice with double extortion and things, but are we, making our situation even worse by sending them even more data? We want to know what it is, right? So, like I said, we know it's 4 bytes, it's little endian, no idea what they are. Are they integers? Are they counters? They look like they're kind of evenly spaced, right? The first one aside, the second two, they're kind of evenly spaced, same amount of data after them. So if we just kind of split it apart, same data, just formatted now, I put some new lines in there. You can kind of almost start to see patterns, but it's still like, what is going on? I don't know what I'm looking at. And if you just almost, start to peel back the layers a little bit, you can say, okay, the section in blue is the same size as the section below it. They're both 8 rows of 16 bytes. That doesn't mean anything by itself, but it's really useful to just start getting a count of your information. Each blob, if you want to call the blue a blob, has some integer in front of it, pre-pending it. In this case, the green correlates to the blue. We have no idea what the yellow is, and the red is like 2. It's who knows. So if we keep, kind of thinking through this, we could say, okay, well, the 2 probably correlates to the number of blobs, right? And this is my thought process as I'm actually reverse engineering this, because this is, like I said, like client data from an infection. Client data has been changed, obviously, but this was the real story. So I'm like, okay, there's a 2. It's probably the number of blobs. What's the yellow? And you kind of have to have a little bit of knowledge here in protocol analysis of some sort, network, file, doesn't matter, encryption. But you start to pick up on these patterns like, okay, if I'm sending data, the 2 pieces of data next to each other probably correlate to each other, and there's probably like a checksum, something involved, right? And it actually turns out that that's exactly what this yellow is. It's a CRC32. It's a cycle redundancy check. It's very similar to a hash, checksum, something like that. So what happens is if we paste the whole blob following the yellow portion into CyberChef and we say, give us a CRC32, it gives us this output. And because we're little endian, which again means reversed, right? If we kind of swap the bytes so that the first is now last, the second is now third, blah, 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 you follow the yellow lines a little bit, you can see it's the same output. So that's your, yep, check, that's a CRC. So, you're kind of starting to understand things a little bit more. And say, okay, well, if the red is a blob counter and the yellow is a CRC, then the data that follows the yellow must be important. That's what the hacker actually needs. And you can figure out that, by speculation, and then you can run some ransomware on some VMs a little bit more and get some confirmation of this, which is exactly what I did. The green is actually the file counter per blob. So the number of files that's affected by a blob is that green counter. In this case, it would be in hex 12B, right? And then the blobs, pure speculation at this point, but we can confirm it, is RSA 1024 keys, which means that, these are actually, this is the data we care about, right? And we can go back and, confirm all of this, and that's what I'm going to walk through. So we need to confirm it's RSA, because it's just a wild guess. I totally pulled that out of nowhere, right? What we can look at is, on the left, the same thing you're just looking at, the blobs. And on the right, that initial driver installation file, right? So you can see the blue on the left matches the blue on the right. There's a little bit of an offset there, but they're identical, right? It's the same exact information. Now, why do we know it's RSA? Besides, it could be anything, right? It's just there's the same data, who cares? But it's the exact same blob, and we can think just by wondering through how ransomware works that we know sometimes RSA keys get reused. It's a unique AES key, but what about the other stuff in the file, right? If we're calling this an RSA blob, what is everything else? Well, let me get to that. But so I'm going a little bit out of order here. Sorry about that, jumping around. But it's RSA, so what do we know? What do we care, right? It's RSA. That means there's no free decryptor. That means this isn't zipping. This isn't XORing. This isn't like, oh, I can make a universal decryptor. It means there's actual RSA keys at play. And if one of you guys has like an RSA breaking decryption algorithm, please tell me about it. You can make a lot of money. But it's unbreakable. It means the attackers are at least somewhat sophisticated, right? You're dealing with like real players here in a sense. And do we have to pay the ransom is always the next question, especially when you talk to the client. You could tell them I broke the encryption, or I know what they're using and I figured out the algorithm and I spent 40 hours doing it and it's great and I know all this stuff now, and they're gonna say, okay, but did I save money, right? So the answer is like, obviously yes, you have to pay because it's RSA, we can't break it. But there's some information that we've gleaned and that we can use, and that is actually super, super useful if you're willing to pay the ransom, which might, you might have to. Let's assume you have to. Since we know each key has a counter, we know that we need every key to decrypt, right? That's common sense. You can't unlock a lock without the key, if picking it is out of the question. But does the hacker need to know the counter? There's no reason, right? It doesn't correlate to anything. We could decrease the counter, might save money if it's like a sliding pay scale. We could put 1 file instead of 1 million files affected. They're probably way more liable to charge you money if it's 1 million files because they think they've hit a data center rather than like a personal hard drive, right? So we know we need every key, but we can probably change that. And then there's this big question of like, do we cheat? Do we manipulate the data? What if we're wrong? All this kind of stuff, right? So the what if you're wrong can be pretty easily alleviated by doing tons of tests here. You can make sure it's the same output that you expect every time, all that kind of stuff. There's not really an ethical consideration here, being that they're hackers and you got hit with ransomware. It's, who cares about them? They're going to get paid less, but, they deserve it. So the kind of, you want to say, yes, decrease the files, be careful, but there's other things that can happen too. And for one, it's, are you sure that you modifying the files is actually getting all the keys? Are you sure that you're not accidentally like changing something? You've made sure that the file counts that are original line up. Because if you did have a data center affected and a million files are encrypted, but you actually, this counter only says 10, then you don't want to mess with that because you've screwed something up. You know, you're missing keys. What about network storage, other mounts? There's all kinds of questions here. Is the attacker aware of storage? Are these keys lining up with your storage? There's always considerations with ransomware whenever you're trying to do any kind of manual recovery of attached storage devices, because sometimes the attackers do really crazy things and you're not expecting it and you end up with corrupt data. If you miss the files, you're going to have to pay again. So consider like, I just completely get rid of the section in blue because I deem that I don't need it. I looked at all the files that use it and I don't want to pay for multiple keys that I don't need, so I just get rid of it and I send it to the attacker, right? If I missed it, I can't email the attacker and say, hey, guy, can you please give me my money back for those files? You know, you're going to have to pay again, probably the same ransom, probably more, actually, if they know that you were messing with things, or they might just not want to deal with you if, you know, they start to smell law enforcement or something else, or they think they do, right? Missing files. You know, if you're missing keys, you really need to reconsider this, because just to reiterate, it's really hard for you on the defense side to remap a destroyed network because you don't know what's been corrupted, what's been affected. It's really easy for the attacker to shotgun blast their malware out, right? They could hit as many servers as you want. They could spread it from 1 machine, 10 machines, and they're corrupting things along the way, maybe, maybe not. But it's easy for them to corrupt. It's hard for you to rebuild. So you need to be really careful about these things. And of course, they're not forgiving again. So, you know, just as an exercise, you can look at the file count and say, does this seem right? Is it 11,000 files infected? Is it 2,000 files affected? What if it said F, right? F is 15. So that's just the things to think about. So, okay, we've deemed what we can. We paid, now what, right? Do you trust them? Probably not. They're going to send you a decryptor next. That's the next step, right? They're going to respond and say, run this. It'll decrypt your system. You're good. The problem with that is they already infected you with malware once. So do you trust them not to do it again? Because, you know, I wouldn't, right? And I want to spend some time talking about this just because it's, can they reinfect you? Of course. What's the alternative if you don't want to run their software, right? The alternative is to build your own decryptor, have someone build your decryptor, you know, whatever, right? Are they going to reinfect you? Who knows? They might be ethical hackers in the other sense of ethical, right? They're black hat, but then they decide to be nice. You know, and there's all kinds of really bad things that they could do. Like, say, for example, I send my output of my scanner, and it says, okay, there's 20 keys, 20 million files, and I pay the ransom, and the attacker sends me the decryptor for those 20 million files, 20 keys, but they lob off the bottom 2 keys because that's 18 out of the 20 million, right? If I haven't done this reverse engineering, I'm not going to know that. I'm going to have no idea. All I know is I sent them data, they sent me back data. What's going on, right? Them lobbing off the files corrupts it, means I can't get those files back. And they can just come back and say, like, oh, you sent me corrupt data, and now the ransom is an extra Bitcoin or an extra 10 Bitcoin or whatever, right? So that's kind of, you know, you still have to interact with them, but at least you can be wise to their, you know, antics if you know what's going on. And this is something we've seen with a couple of people, clients, even not clients, you know, just sometimes you read about it online in blogs or whatever, and people say, well, the ransom was 0.1 Bitcoin, and then they came back and they said another 0.2 Bitcoin, and then they said another 0.5, and eventually I paid 3 whole Bitcoin because I just had to keep going and going and going. You know, it happens, right? So enough of the kind of, you know, back to the technical, a little less of the preachiness, right? But okay, the output of what the attacker sent me back. What is it? So it's more base 64. This part looks familiar. You know, it looks actually really familiar if you look at it spread out the same way we did before. We see there's a 2 at the top again because we sent 2 keys, we got 2 back. We can assume it's a CRC in the same place, and we can double check that, and it is. And then we know we can look at the next blob that's not highlighted in blue this time, but starts with the AA at the top, right after the yellow, and it matches the before and after, right? The before being what we sent to the hacker, the after being what we got back. It's the same exact data. And you know, this might cause you pause at first. You might say, okay, why did they send me back the exact same data? Did I get scammed? which is always a consideration. But no, in this case, you didn't get scammed. This is what you wanted, because what's happening is this is the RSA ciphertext of the encryption key. They need to know just as well as you do what key associates with what file, and there could be millions, right? They could be, and it is in this case, one key per one file. They do it automatically, randomly, doesn't matter to them. There's no master key, anything like that. So they need to associate that ciphertext in the encrypted file with the new key they've given you back, right? So they're going to give you the same data. This is what you want. After that data, after that same blob that we've already verified, you can say, okay, well, it's followed by 32 bytes. Great, right? 32 bytes, hooray. But AES keys are 32 bytes. You can make a pretty simple, assumption here that these are AES keys. I should say AES 256 keys are 32 bytes. It's in the name. But then you can say, okay, we have the key. Great. Now let's go back and look at the file again. Now, we know the files are using RSA to encrypt the AES keys, and the files are encrypted, and they have the file name in them. That's great. That's a ton of information. We don't know anything else about it. We don't know what all this extra data is. We don't know where the file starts and where it stops. In theory, you'd say, okay, it starts at the start and it stops at the end, but that's probably not true because there's at least some extra data in there, right? So it could get manipulated in all kinds of weird ways. We know where the file name is. We know kind of what I'm going to call the header of the footer. Weird name, but it starts with that BV0Y. The footer, just the end, and it's the header because it's the start of the end, right? There's the header of the footer again, just for clarity. And then there's some weird counter. And I'm calling it 16 bytes because I don't know what it is. It could be whatever, right? It's just 16 bytes in a row, and the reason that I've kind of padded that 16 bytes off is because it stands by itself when you start to compare it to the file name and the header of the footer and all this kind of weird stuff. And then right after that 16 bytes is where the RSA key existed. So you're kind of saying, okay, I know where the RSA key is. I know presumably where the end of the file is because I know the file name, and it's probably before that and all this kind of stuff. So this sum counter, we don't know what it is. It's another integer, presumably, right? I'm calling it a counter because it's very small. Normally, if it's like some large integer that's random or CRC, something like that, it's going to be large. It's going to be, have better entropy than 0. This one is just 0E. It's 14. That's very small, right? So the consideration is like, what is this being used for? What's happening here, right? What is this counter? And we can actually figure out that the first 16 bytes is the IV, because we're assuming it's AES. AES uses 16-byte block ciphers, and they have 16-byte IVs. And the counter is actually just padding, because we know that we have to associate things back to the encryption algorithm, because the goal for us and the attacker is to decrypt. So we know that we need some number of padding bytes between 0 and 15. In this case, happens to be 14. And we know the IV, and we know the key, so we can try to decrypt. So there is a little bit still of extra speculation of like, what is this? What about the end? There's still 4 bytes on the end. What is it important? Do I need to know about it? Am I going to like destroy my system? It's like maybe still a counter, but it's kind of simultaneously small and big, right? 58 hex. That's not a small number. It's also not like a 4-byte number. So you're like, what is going on here? It's not padding. It can't be a file counter because it doesn't match the one that we looked at previously. Is it important? Can I throw it away? There's tons of considerations, right? It turns out that, it kind of matters, but not really. And we can figure out what it is. This is pretty grueling, actually, for me to figure out because I was like really concerned I'm going to corrupt some data, right? So if we start to look at how big the footer is in general, we know we have a 26-byte header, 16-byte IV, 4-byte padding, 128 RSA, and then 4 weird bytes. And honestly, this is just counting by hand. There's no like special magic going on here. And if we add all those up, we get 178. Great, 178. What the hell? Before those, you have the file name and a bunch of weird stuff, right? So this is before those, meaning you start at the end, go backwards 178. Well, some more quick math. 58 hex is 88. 178 plus 88 is 266. If we go back 266, that's the start of all these weird zeros. So we don't know what any of those zeros at the top are either, but now we know, okay, that weird counter at the end leads us before all this other weird stuff, so that's where the file ended. We can cut off all this crap, and we can say, the file is the rest of it from 0 to down. So you might say, okay, are we done? And there's a couple reasons that the answer is no. Yes, you've solved this part of the protocol. There's actually a lot more to it. You still have to write the decryption, though. You have to really, really, really worry about writing that decryption, because encryption is really hard to get right. And what you have to consider is, did the attacker get it right? Because if they messed up on their end and you do it correctly on your end, that leads to corruption. You almost need to mess up in the same way, right? You need to kind of replicate their encryption before you can decrypt it to be sure. You need to make sure that you catch any bugs or corruptions. I've seen attackers that accidentally delete data, and it ends up kind of working out for them because they have some weird off by one error, and it replicates. It's crazy, but somehow they've ruined their encryption, and it ends up with the right data anyway because they have the bug in both the encryption and decryption stage. You probably are going to want a support contract if you're doing this with your client, and that's obviously way more businessy than technical, but you're going to want something in the works there because you're going to have to keep supporting this if you're doing manual decryption for them. There's no way that's a one-time engagement. You go on and say, okay, here you go, guys, you're done. I'll never speak to you again because everything's perfect. That's not the world we live in, right? You're also going to obviously want to fill them in as much as you can on the technical details. They're probably not going to go for it, but you need to tell them. And the next consideration is network shares. But what I actually want to do real quick is show a couple more slides that I have disabled. So just bear with me for 1 second. I've disabled a whole ton because I didn't think I was going to get to them, and I've been talking really fast. Skip slides. Okay. Cool. So there's another problem. You might say, what? We just figured everything out. The problem is that there's actually not just one protocol with Dharma. There's two, and it's really different. Dharma actually treats bigger files way differently than smaller files. Smaller files are that protocol that we just went over. It's pretty straightforward. It just says, okay, great. Encryption key, find it, decrypt it. It's pretty straightforward. Anything that is 24-bit shifted 16, and that might seem like a really weird number, whatever. Anything larger than that file size, they encrypt it completely differently. So here's a sample file. This is the beginning of it. You might notice it's all zeros. That's not encryption. It's zeros, right? That how do you recover from data being deleted? So your first thoughts are panic. And besides that, you think, okay, is this data corrupted because it's gone? You can't turn zeros into not zeros. It's super low entropy, obviously, because there's nothing there. So it's not AES encryption. It's not compressed because compression wouldn't do this. It wouldn't have this many zeros. That's the antithesis. What is it, right? Well, the first question, once you've calmed down because you're worried about your career being over, when do the zeros end, right? How many zeros are there? Do we ever actually get real data? And the answer is yes. Eventually, at this suspiciously round number of hex 4,000 or 40,000, we get data again, which is great. The suspicious number is kind of weird because why would it just happen to be a perfectly round number like that? And what's even weirder is, this is still not encryption if we look at it. It's a little bit hard to tell in this example because I think this is some Microsoft Office product that they do compression inside of the file, but it's low entropy. And you're thinking, okay, well, is it plain text? Is it corrupt? What's going on? And the answer is that it's actually plain text. I found this out just by scrolling through a bunch of files like this, and eventually I found English words because it was a Word doc, and eventually you get to the markup that's the real part. So if you keep scrolling through the file, eventually the zeros come back, and now you're back to panic because you're oh God, it's just corrupt. The zero, for some reason, the first part of it's gone, then there's data, and then there's not data, and then they stop, and then they come back, and there's just all these zeros. So the question is, what do we know about the zeros? Because we know they're everywhere. There's data in the file, but it's also gone partially. So the only things we know about them are their sizes. They start at 0, they go down to 40,000, then they start back up at 11 FB55, which I hope doesn't mean anything to anyone because it doesn't mean anything to me, and it's a weird number. And then the same thing, 31F200 doesn't mean anything to anyone. That's not any range of numbers that anyone cares about. But if you do some subtraction and you realize that each range of number is actually hex 40,000 size each, that gives you a little bit of hope because that tells you that it's specifically made this way. and there's just always the same number of them. If you look at the very end of the file, it's the same thing. It's a ton of ciphertext once the zeros end. It's encrypted. It's not plain text in this case. It's back to encryption. So we have this weird situation where we're dealing with data being deleted, data being encrypted, and data just being left alone, all in the same file. This sets alarm bells off for me, at least, and probably a lot of people, because you're like, what do I do in this situation? It's not a decrypt. It's not a decompress. It's not a anything. You don't know how to handle it, right? So what do we know? Again, just reviewing. There's a ton of ciphertext. This is nothing like the other protocol, but let's look at the footer of the file again, right? Let's go back to what we know. We know where the file name was. We know all that kind of identifier stuff, and we can say that this part kind of looks the same. It's still the same. I'm calling it again the header of the footer, but that part's the same. There's still a file name. You can see it kind of starts with PNG. That's the end of the file name. There's still an IV. There's still padding. There's all this stuff, but the padding is 0 bytes. And that's possible in encryption. Sometimes it just happens that way, but it's pretty unlikely. Every file that has this protocol was always 0 bytes. That's the unlikely part. So that means that every single time this happened, there was never any need for padding, which kind of leads you, if you know about encryption and why padding happens, you'd say, okay, is it block aligned, right? So the answer to is it block aligned is yes, because there's no padding. That's by default. You know the answer to that. But it just so happens that there's C0000 bytes, and that 40,000 hex, which is the number of zeros, if you times that by 3 because there's 3 of them, then you get the same number. So this is a little bit weird. And then you kind of start to piece it together as you stare at the wall for 6 hours straight trying to figure out what's going on. You have C0000 whatever total bytes of zeros, and you have the same number of bytes of ciphertext. And you could say, okay, the zeros must line up with the ciphertext. Obviously, they've just relocated it somehow. So the way this works, the way that it ended up working, once you figure it all out, is that 24-bit shift 16 to the left, that's C000 as well. Same thing. So any file that's larger than that takes this protocol up. And when they take this protocol up, what they do is take that many bytes, and they just encrypt that many bytes. So rather than encrypt the whole file, they only encrypt, whatever, it might be 3 megs, I think, or 1.5. I have it, no, 3, because it's 1.5 times 2. So what about the rest of the file? You can say that it's plain text. Great, we saw that earlier, but it's corrupt. So, you're kind of asking questions now, why did they switch their protocol up in the first place at all? If they were worried about people realizing how the first protocol worked, they wouldn't use it. They would have done something else. And it was still pretty weird. So, they're not probably worried about that. So what's the reason that they just change things up in this obscure way? And the answer is a little bit of obfuscation. They're just trying to change it up, make their own protocols, and do cool things. But really, it's speed. This isn't any sort of amateur hour buffer overflow, which might be the first thing that some people, jump to is oh, whoops, they accidentally zeroed all their data. It's actually just that they wanted to be quick. So if they're encrypting a 1 megabyte file, that's very fast. Obviously, 1 megabyte is not a lot of data these days. If they're encrypting a 2 terabyte file, or even smaller than that, say a 20 gigabyte file, 5 gigabyte file, that takes time. And the more time they take, the less files they get to before you notice. And your data center might go down or something, your SQL server, because they're encrypting it. You're more liable to notice that, and you're immediately going to go check the rest of everything out. So really what they're doing is speed. They want to get in and out, encrypt everything on disk as best as they can. And what they're doing is encrypting only part of the data and then rearranging it so you'll never notice it. If you open this up in a hex editor like I did, you're going to notice a bunch of zeros and you're going to say, oh, the data's gone, right? The only reason that we find this out is because first we did the easier protocol and the smaller files, and then we made it all the way here. So, okay, are we done? Not quite still, right? We kind of know that the zeros represent encrypted data, and we know we have the encrypted data, and we know it uses AES, but there's still a lot of questions. We don't know where the plaintext starts and stops. In this file, we could say, okay, we found the bytes that it starts and stops at, but it's not the same for every file. It's almost randomized. It seems to depend on the file size, maybe, but they're not evenly spaced. There's no sort of, it's always 5,000 bytes in or anything like that. It changes based on the file size. And obviously, the attacker has to know. I mean, they're not just pulling data out of thin air, so there's an algorithm involved. And just saying there's an algorithm doesn't tell you anything because everything's an algorithm, right? But there's obviously something to figure out here, something to RE. So it's kind of right in front of our faces, in, again, a super obscure way. So if we look back at the ranges of where the zeros were, what's going on there, we can try to figure things out. We've got the ranges back up. So of course, my red square is a little bit messed up. But if you look at the first red square, C00F23100, you can see it's, I don't want to skip ahead again. It's the same numbers as in the bottom left, right? The red boxes, the attacker has put the data in the file saying where the offsets are. So, this gives another problem of we have to be able to find the offsets in the file, but it's at least a little closer. We don't need to recreate the entire algorithm and figure out any weird randomizations or shifts or seeds or anything that they used. All we need to know is it's stored in the file, right? And of course it's stored in the file because the attacker needs it as well. So again, are we done? Yes, but no, right? And I kind of talked about this stuff before. The decryption has to be written. It's really hard. This one is even crazier because there's all kinds of problems. Like, did I get the index right? Is my file size calculation wrong? Is there another protocol? There's not, thank God, but there could have been. So there's all sorts of things you need to worry about because you're going to corrupt data. Did the attacker corrupt data? Was the file being written to while it was being encrypted? All this sorts of stuff, right? So, there's all kinds of problems. So the last, I talked about network shares before, but just to reiterate, remember the missing files, and that this is because if we consider the fact that there's missing keys, something's gone, the sizes don't line up. If you consider your network, you probably have, if you're a corporate network, tons of shares, tons of mounts, tons of, you have Azure Cloud, AWS, local NAS, whatever you got tons of stuff that's mounted in different ways you might not even know. The hacker doesn't know or care either, and they might infect servers 1 through 3, they might infect just server 2, they could do whatever, and that's going to blast out encryption everywhere. How many workstations had access, all this kind of stuff. So these are really, less of the encryption kind of questions you have to ask, but more of the just normal use case questions, like how much of my data is encrypted. So I've had people that I know, I don't want to say clients because they weren't, but I've had people that I know that have done this sort of thing and said, okay, I found a decryptor, I want to run it, but they don't back up all the data first because it's 20 terabytes or something more than that. And they run their decryptor that they found or wrote or whatever, and now their servers are hosed. They're completely gone. What are they going to do, right? The data's gone. You can try to decrypt it, but it was corrupt, so good luck. And it's just those kinds of considerations that you have to think about, because what happens? You go from a ransomware attack that potentially you could get double extorted, you could have tons of problems with, but you could pay money, probably a large sum of money. You could pay money and fix it, or you come in here with your hammer and start smashing stuff and try to fix it yourself, and now you're at a state where you can't even pay the money and you're just gone, right? So that's pretty much what I've got. So I know I actually went way faster than I expected. I talked really fast and about some really dry stuff, so if anybody's got any questions, please, good timing. And I'll throw my email back up also, because people generally want to talk shop about things. So shoot me questions. Please don't ask me to come decrypt your ransomware for free. I probably can't. That's it. Does anybody have any questions before I kind of meander off? Yeah, so I threw my email up here also, just if anybody wants it. So it's mostly experience. I did a lot of malware protocol analysis in the network side before I did any ransomware related stuff. So there's a lot of correlation of storing things for network traffic and storing things for files, because it actually usually wraps back to C structs, and a struct in C just being mapped directly to memory or to disk. So it's mostly manual at this point, just with experience. You could, write some algorithms, and there's tons of tools that do things. It's really similar to if you've ever run strings on something, it pulls out encoded data to look for certain patterns, like finding integers, for example. If I can just skip through a million slides now. Finding the integers. Like the 2 is really obvious because it's, for one, it's at the beginning, but it also has 3 zeros after it. And if you know you're dealing with little endian, then you know those are actually like the upper bits of the integer, bytes, whatever. So you could write something like that that's going to search for certain padded data that pulls out integers and then maybe says like, okay, this is probably an int, and this is the blob that happened after it up until the next int, that kind of thing. And that could help expedite the process. The problem is that when you're dealing with ransomware or malware executables, just because they're the same type, like these are 2 Windows ransomware executables, they're not necessarily going to do anything related to each other except the encryption. So you can try to build tools that do things automatically. In my experience with reverse engineering specifically, it's really manual because it's hard to get a perfect generalization just based on how different, different binaries act. Cool. Does that answer it, I hope? Great. Anybody else?
See, I can cheat. I have the mic. Would you say that the bad actors are adapting to the fact that we're getting better at this? And if so, how well are they adapting? I mean...
Yeah, absolutely. So ransomware, I mean, just like any malware, in my experience, there used to be a lot of really bad ransomware, badly written, bad tradecraft. And as that kind of got handled, because people would come up with, one decryptor, one size fits all, it decrypts everything for everyone, they would adapt to that by saying, okay, now it's 1 key per file. And then they'd say, okay, well now we're going to always scan your network first before we launch our attack because we want to get in there. Newer ransomware families do things like disable security products, unload drivers, reboot your machine into safe mode. I've seen ones that they actually bring their own virtual machines and then they move your files to the virtual machine and do the encryption there and then move them back. So they're definitely adapting. It's a little bit of a cat and mouse game, but they're already using like what's considered like military grade encryption, which is just using encryption properly and using like OpenSSL for RSA or something instead of doing it themselves. So they're definitely adapting. It's kind of a scary world out there, but the good side is adapting as well. Antivirus and EDRs and all sorts of things are you're starting to see a lot more ransomware protection specifically. That's what I do, and I don't want it to turn into like a sales pitch type of thing, but I work on a product that's like automatic ransomware prevention, detects the behavior, stops it, that sort of thing. So definitely a lot of advancement on the attacker side though. Anybody else? I'm not seeing anything, so I'm just gonna hop off the stage here. But thanks everybody for listening, and that's all I got.